Good evening, madam.
Good evening. We'll wait for some time and then I'll start.
Okay, ma'am.
Okay, I'll start. I'll be sharing the screen. So, good evening. Welcome to yet another problem solving session for the course Geographic Information Systems. The course instructor is Professor A.K. Saraf from IIT Roorkee, and I'm the teaching assistant Anjana from IIT Kanpur. So today, although I have put it as week 12, we are mainly going to discuss week 11 uh, lectures, the remaining part of the week 11 lectures. And since you have not yet, the deadline for submission of week 11 assignments is tomorrow, so the solutions are not yet there. So I will not be discussing that problems today. We'll be doing that in the next session. So, yeah. Today we are primarily going to focus on the digital elevation model, which is based on surface hydrologic modeling. So, as I said, like in GIS, our ultimate aim is to create certain models which are very much realistic and which helps us to tackle a lot of situations without having to go to the ground. Rather, you can just prepare such models and estimate all the things that needs to be done. So this surface hydrologic modeling, like um, it's sort of like it's we input the dem and then we do the modeling, so it's like based on the digital elevation model. So basically we have two models, digital elevation model and the surface hydrologic model. So model basically means that the like in case of the surface hydrological model, we are basically what are we modeling? We are modeling the flow of water across a surface, and that surface here is the digital elevation model. So that needs to be understood. Okay. So what I'm trying to say is we have two models here. One, obviously, the DEM, and the other is the surface hydrologic model. Okay. Now, what is the connection between these two? Like surface hydrologic model tells you the uh, just a minute. Okay. The flow of water across a surface. Okay, that is what the surface hydrologic model tells you. Now what is the surface? This surface, where do you get it from? We get it from the digital elevation model. So that is how we are actually combining these two together in order to understand or better understand the flow of water in a particular area. So we are basically using one model to model the water flow over the surface and the other model as the surface. Now, as we know, like the shape and characteristics of the Earth's surface is useful in many fields of study, especially in earth sciences, hydrology, geography, civil engineering, and all these things. We need to understand what the shape of the Earth is and its characteristics is. Because if you remember, when we were doing the map projection or when we were studying about these hillshade, like all those things that we were studying earlier, so in that we actually had to have an idea regarding the shape of the earth, the characteristic of the surface, all these things needs to be known. So this is specifically to such studies. So these shapes and characteristics of the surface and like which model, which data can represent all these things together combine the digital elevation model. And it also allows us to like in our once we understand the characteristics of the surface, it allows us to see how changes in composition of an area is happening and how it will happen in the future. Like for instance, we have these land cover maps, like they are a good example of that. Okay, so LULC, we call it as LULC. So what we do is basically you have an area. Okay, so I sort of created an LULC, land use land cover map for that area in the year, let's say 2011. Okay, so I created something. So this LULC map, like that map consists of vegetation, like forest cover. Then it has built up uh, land, river, all kind of things. Like this is just I'm saying some examples, but I'm just saying that okay, I have a map, LULC map prepared for a particular area in the year 2011. Now, if I again generate a similar map in 2021, obviously 10 years has passed, a lot of changes might have come. So that change can be well accounted for by comparing these two maps. Okay, so this is what I'm trying to say, like what all changes a area has experienced over a period of time. If in order to understand that, we need to have an understanding of the characteristics of the earth surface or other parameters. And then, especially in case of surface hydrologic modeling, we are basically trying to understand how the water behaves, like how it is going to flow on the over the surface, earth surface, how it is going to create different features like geomorphic features, or boundaries, that kind of thing. So basically, these two models, that is the digital elevation model and the surface hydrologic model, it will allow us to predict what would happen if we, make some changes on the ground. Because see, it's not possible for us, as I said, the flow of water, it's not restricted to a kilometer or a two, right? It's going to be over a very huge area. So it's not possible for you to reach every single point in order to understand what a particular action can have an impact on that flow of water. So if you have a good model, a surface hydrologic model, then basically you can actually predict what, like suppose you are going to build a dam, or let's say you are going to like say create some rerouting of that flow or something like that. So you can actually instead of doing that, before doing that, you can actually predict what your action can uh, cause, what change it can bring about. A good example is the deforestation. Okay, like if you cut a lot of trees in an area, then what happens is, like the trees, in their presence, the soil's moisture retention is quite good. But then if when you cut the trees, that actually affects the soil moisture condition. And if that condition is changed, like that water holding capacity or soil moisture in a particular area is changed, that is definitely going to bring changes in the soil erosion, which in turn might affect the groundwater. So it's kind of like a chain thing, like it affects one thing and then because of that it affects another thing, so it just continues. So such things and all, you can actually utilize GIS for that purpose. So any change on the surface of the earth, in terms of vegetation or drainage or even elevation change, that will all bring some effective changes in one way or the other. It may not be seen immediately. It can, as I said, it can be seen over a period of time. But then, yeah, that will definitely have a effect. I'm just telling you all these things so that you can just have an idea like why this modeling is quite important, especially in the current scenario. So before getting into the surface hydrologic modeling, we need to have a little bit of idea regarding the drainage systems. So if you already know, even then let's consider this as a revision so that because some of these terms might be used later. So at that time it should not be that confusing. So it's better that we discuss it now itself. Okay, so the drainage systems, it's basically an area upon which water falls and the network through which it travels to an outlet. So it's basically from the starting of a river, let's say it starts from here, it goes, it spreads out, whatever, and then finally it has an outlet. So that entire thing is called that river's drainage system. The flow of water through a drainage system is basically a subset of the hydrologic cycle. Like we are already familiar with the hydrological cycle, like how the water is like it comes to the earth by precipitation and then it goes by evaporation. All these things we know, right? Evapotranspiration is there, groundwater flow is there. So along with all these things, the water surface water flow or the water flow in a drainage system is a subset of the hydrologic cycle. The surface hydrological model, as I said, focuses on the movement of water across a surface, how the water moves on the surface. So the drainage in a basin that we say, it is basically an area that drains water and other substances to a common outlet. Okay, so here we have an example of the drainage basin. Let me just hide. Okay, so here is the outlet. it has come and it has spread out and all those things, and then you have outlets over here. And other common terms for the drainage basin include watershed, basin, as I said already, catchment, or contributing area. This you can, it's just for like if in future if we talk about watershed, it's more or less just we are talking about the drainage basin. So it's better to just keep in mind that these are also other names for drainage basin. Here we are just discussing certain terms that are used so that in while discussing the modeling, if again these terms come in, you don't get confused. Okay, so pour point is basically the point at which water flows out of a watershed. Okay, so this is the watershed, this complete thing, and then this is the pour point where all that water which is present in the watershed is flowing out. Not all the water, I'm just saying where it flows out. Okay, usually the lowest point along the boundary of a drainage basin. So most of the time that will be the lowest point in a drainage boundary. And what is this watershed boundary or drainage divide? That is the boundary between two basins. Like it can be of one river system and then another river system. So between that you will have a watershed boundary. So here we have a traditional watershed delineation map. Before that, there's another thing. Okay. Since we were discussing this, I think I'll tell it here itself. So the network through which water travels to the outlet, we can see it looks like a tree, right? With a tree with a lot of branches and everything. So we say the network through which the water travels to the outlet can be visualized as a tree with the base of the tree being the outlet. Okay, so this can be considered as the base, and then from there, actually this is the outlet. Okay, so it's basically coming from here, but just to for imagination purpose, we consider this pour point or the outlet as the base, and then we have the branching out. So this is like this we'll further discuss when we are discussing the stream order. Okay, so the branches of the tree are called as stream channels. So whatever branches that you are seeing, like this one single thing, if you consider like this, then these small things are the stream channels. So the intersection of two stream channels is referred to as a node or a junction. So this term we have used earlier also. So where that intersection is happening between two stream channels, we call it as a node or a junction. I know I'm just discussing a lot of terms, but it's better that you have a little bit of understanding of what these are. The sections of a stream channel connecting two successive junctions or a junction and the outlet are referred to as stream links. So basically we have talked about these terms, that is stream channel. Then we talked about node or junction. Then we talked about stream link. So this is a traditional watershed delineation. This is the watershed that you can see, this brown one. Okay, that has been done manually using contours on a topographic map. So based on the contour that was already there in a topographic map, this watershed was delineated. So the watershed boundary, it can be sketched by starting at the outlet point and following the height of land, defining the drainage divides using the contours on a map. So as I said, this outlet is mostly it will be the lowest point. So from that lowest point, we will trace the slope. Okay, like height of the land. So how it is increasing? Definitely, like where that outlet is would be the lowest point. So we sort of trace it in the according to the height, and thus dividing the or defining the drainage divides. based on the contours, because contours tells you about the elevation, right? So based on that you can do it. But this was this was how it was done earlier, like when you do it manually. And so they uh, got used these topographic maps in order to do the watershed delineation. This brings us to the main topic for today's discussion, that is the digital elevation model based surface hydrologic modeling. So just a minute. So when you do a surface hydrologic model based on the DEM, first and foremost we need the DEM, right? The digital elevation model. So because from that only we are going to do the remaining things. So first and foremost you require a digital elevation model. And here we basically have to put an assumption, quite a big assumption, when we are doing this digital this surface hydrologic modeling. So the assumption is that whatever the precipitation will occur, it has to come out through the outlet. Okay, that assumption, based on that assumption only, this modeling is done. So what is the assumption? All the precipitation occurring has to come out through the outlet. Okay, so that is the assumption. Based on this assumption only, we are continuing with the remaining things. So this you have to keep in mind. It's quite a big assumption also. It's not possible all the time that all the precipitation that comes on the surface is going to go through the outlet. But we have to make that assumption in order to simplify a little bit rather than complicate the entire thing. So we are basically assuming that there is no loss of precipitation. That is basically we are not losing any of the rainwater, neither to the atmosphere like through evaporation or evapotranspiration kind of thing like from the plants or through groundwater. So we are not losing the precipitation in any of these ways. Rather, it is only coming through the outlet of the drainage. So this is the only assumption that we are keeping, but it's quite a big assumption in case of surface hydrologic modeling. And as I said, the input that we are giving is the digital elevation model. Okay, so this is the input that we are giving. So first thing we need to do is we determine the flow direction. Okay, so that is the first thing that you do. Once we get the flow direction, we will identify the sink. Okay, why we need the sink is because based on these assumption, because we are saying that the precipitation has to come out, but at the same time it may not be the case. So the sinks can be sort of like an error within the digital elevation model. So in order to determine that, we also need to see what the sinks are. Then if there are sinks, we have to fill it. If there are no sinks, then we have a depressionless DEM because all the depressions will be removed. So basically if we will be using a 3x3 window like we were discussing last day. So we use that 3x3 window, and if any cell in that digital elevation model, if it is found to have water that will not flow out of that cell, then we will then it is labeled using the surrounding 8 cell values rather than keeping it like that. So because our assumption is what? Whatever precipitation is coming is going to go out. So we'll remove such small depression artifacts. So once the sink identification, like once we have a depressionless DEM, then we go for determining all these things: flow accumulation, flow length, like we are going to discuss all these things, but just for your understanding, I'm saying we start with a DEM input, then we determine the flow direction, then we determine what all sink is there in order to account for the assumption that we made. If there are sinks, we'll fill them. If not, we directly go to the DEM. Like we start with that DEM. Okay. So then what we do is we calculate the flow accumulation. And we are going to discuss each of these terms in the subsequent discussion, so you will be able to understand it a little better. And in flow accumulation itself, we are going to see the stream order, stream to feature, stream link, then flow length, snap pour point, watershed. So we are going to discuss all these things. So the most common digital data of the shape of the Earth's surface is cell-based digital elevation models. The digital elevation models are the best uh, digital data that you can have regarding the Earth's surface. This data is used as input to quantify the characteristics of the land surface and surface hydrologic modeling. Further, the accuracy of the DEM is determined primarily by the resolution. Okay, because like depending upon our need, we need to have a good resolution digital elevation model. If not, like as I said right now, to account for that assumption, if your resolution is low, then you will not be able to actually identify the sink properly, then it's not going to be possible, right? So I'm not saying very high resolution data, but according to your requirement, a good, a considerably good resolution DEM should be used or utilized for this purpose. Other factors which affect the accuracy are data type and the actual sampling of the surface when creating the original DEM. So that is not actually in your hand regarding how that sampling was done, but then you can actually input more information and then sort of refine the model. So the errors in the digital elevation models are usually classified as either sink or peak. So a sink is an area which is surrounded by higher elevation values and is also referred to as a depression or pit. So that is understandable, right? You have, like, basically, if you have a lot of cells in the grid, okay. Okay, so we have a grid like this, and let's say I'm just giving a random number. Okay, so I'm giving here a number of, let's say, 6, 5, 6, 7, 6, uh, again 6, 5, 6. I'm just randomly giving, and then at this point we are having, let's say, a 3 or a 2. What does that mean? Like if suppose these numbers represent the elevation, then that means that this area is a sink or a depression or a pit, because compared to the surrounding it is less, which means compared to the surrounding it is at a lower level. Okay, and this identifying that sink tells you that okay, this is an area where a possible internal drainage can happen, that is that whatever water has come will go into this drainage, not all but a little bit of it. So such things can be understood when we are creating the model. And what you have to keep in mind is some of these sink may be natural, particularly in case of the glacial or karst areas, although many sink are imperfections in the DEM. So this can be natural because in glacial terrain, if you are familiar with geomorphology, then it's just a fact kind of thing. Like if you have a glacier that is flowing, let's say this glacier is going like this, and if it has some kind of rocks or stones stuck at the bottom of it, what it will do is when it is going to erode the surface, and then later on it will generate such depressions, small depressions or pits, something like that. So that is something natural, right? And even in karst topography, karst areas are where you have a lot of limestone features. Like it's a limestone terrain, and because limestone can be subjected to erosion fairly more by exposure to the precipitation and stuff. So in such regions also you can have natural sink. But another thing that you have to keep in mind is unless that region is not glacial or karst and it's a completely normal kind of location, then you have to understand that if you have any kind of sink present, that could be a imperfection in the dam that was generated. Okay, so these are few exceptions, but then most of the time the sink that you see would be imperfections in the digital elevation model. So that needs to be filled before preparing the surface hydrologic model. Similarly, a peak that, like as I said here, errors in DEMS are usually classified as sink or peak. So we discussed about sink. Now we are talking about peak. So likewise, a peak is an area which is surrounded by cells of lower value. So as I drew earlier, so unlike that, let's say we have a grid again. Okay. Now here, earlier what did I write? Like big numbers surrounding a small number, right? Now instead of that, right now I'm having a 7 here. Then let's say 2, 3, 1, 1, 3, 1, 2. This is just random number, okay? I'm not saying this is the one, but only to for you to understand. So surrounding values are less compared to the center one. So that particular cell is considered as a peak, an area which is surrounded by cells of lower value. The surrounding cells are of lower value. These are more commonly natural features and are less detrimental to the calculation of the flow direction. Compared to the sink, the peak is not going to create much of a problem while you're calculating the flow direction because that's not going to affect the water as such. So, peaks are not a big issue, but even then, it's a source of error. So, that's what they're saying. Errors such as these, that is basically peak and sink, but more than like compared to peak, more problem is caused by the sink. So, they should be removed before attempting to derive any surface information in order to determine the flow direction. Sink being areas of internal drainage prevent downslope flow routing of water. So what happens is if you have sink present, then that continuous flow, like modeling that continuous flow is going to be difficult because if you have a sink present, then that effectively tells you that water is going into that sink, which means it, there will be a disturbance in that flow of water in the downslope. So and thereby affecting the flow direction of the water. So that's why we need to take care of this. So here, okay, we have a good example of a sink. So this blue color, that is a stream, and this black one is a elevation, 100-meter elevation contour. So this depicts that it is at a 100-meter elevation. So the surrounding region, everything is like 100-meter, and then here you have 95, 97, 96, 98, 99, all those things. So this is a sink area. Okay. Cells containing the contour are assigned the value of the contour. All other cells are interpolated. Sinks are always possible in areas where contours converge near a stream. So a sink is a cell or set of spatially connected cells whose flow direction cannot be assigned one of the 8 valid values in a flow direction raster. The problem with the sink is that, see, you need to have a flow direction, right? So that value cannot be assigned because in a sink, the water is going to go down. So that flow is restricted, right? So that's not possible to assign a value for the flow direction in a raster. This can occur when all neighboring cells are higher than the processing cell, or when two cells flow into each other, creating a two cell loop. So what happens here is that from 100, like it's going to 95, then it's going to 98. So it's like flow will not be like it's going to come down and it's going to go up, right? It needs to have a slope, down slope direction at least, if not a flat terrain. So that is not possible if in the presence of a sink. The number of sink in a given DEM is normally higher for coarser resolution DEMs. That's what I was telling you. Like if you have a finer resolution DEM, then it's easier to determine the sink, and possibly the sink number will also be less in a finer resolution digital elevation model. But when it is coarser resolution, uh, when you determine the number of sinks, that is going to possibly be a bit more higher uh, when compared to finer resolution. Another common cause of sink results from storing the elevation data as an integer number. This can be particularly troublesome in areas of low vertical relief. It is not uncommon to find 1% of cells in a 30-meter resolution digital elevation model to be sink. So this problem is that when you put it in just integer number, the problem is that low vertical relief areas will not be actually considered as a relief, but rather they will consider it as a sink. So that is one of the reasons why in a 30-meter resolution digital elevation model we find at least 1% of the cells as sink, because that's a bit coarser resolution. But at the same time, as I said, it's also dependent on the purpose that you're doing. But in hydrological model, it's always better that you have a finer resolution digital elevation input. So here we have an example uh, of a digital elevation model. So when this digital elevation model is subjected to the identification of sink, you can see we have a lot of red dots over here, right? Over here, okay, different along that drainage we can see a lot of red dots. These are the identified sink. So 186 sinks have been identified with the digital elevation model in the background. So some of these sink can be single cell, or some can be a set of cells. It's not necessary that it should always be a single cell. It can be a set of cells too. Next is deriving the runoff characteristics. So first and foremost, we need to delineate the watershed, okay, using the surface hydrologic model, or we need to define the stream network. So we are going step by step. So that's why, like sir also mentioned that the surface hydrological model. Just a minute. Yeah. So as I was saying, the surface hydrologic model, it's basically sequential modeling, like we go in sequence, okay? Sequential model. So there will be like a series of steps. We follow each one by one, and some are necessary steps, some are optional steps, and depending on the characteristics of the DEM that we have input. And another thing that you have to keep in mind is that the flow across a surface will always be in the steepest downslope direction. Like that is something we observe on a daily basis when you see a river flow or something like that, or even when you just you know pour water on a ground, you can see that it moves in the steepest downslope direction. Once the direction of flow out of each cell is known, it is possible to determine which and how many cells flow into any given cells. Okay, so that's how we determine, because we are always, when we are talking about this digital elevation model, it involves a lot of cells, like a lot. So we need to uh, determine the direction of flow out of each of that cell, and also determine like where that flow is going to, like into which cell that flow is going. Based on this information, we can actually define the watershed boundaries and also the stream network, like in what direction it is moving, till which portion is that watershed covering, all those things. So regardless of the goal that you have, we are always going to start with an elevation model. The elevation model is used to determine which cells flows into other cells that I said. However, if there are errors in the elevation model, or if you are modeling karst geology, there may be some cell locations that are lower than the surrounding cells. So this is another thing, like as I said in the initial part itself, like most of the sink are like some you know not natural ones. Like in a digital elevation model, it might be due to a problem with the resolution, or in the identification of such things. That is the like general scenario. But in case of a terrain, like digital elevation model for a glacial terrain, or for a region with karst geology, in such cases, there may be some cell locations that are lower than the surrounding cells, and that is normal in that location. It's not something which is an artifact or something like that. So, in such cases, what happens? All water traveling into the cell will not travel out. These depressions are called sink. The hydrologic analysis tools allows you to identify the sink and give you tools to fill them. The result is a depression less elevation model. You can then determine the flow direction on this depression less elevation model. So from all these things, the only takeaway that you have to keep in mind, the main takeaway that you have to keep in mind is, we are working with a digital elevation model, and that digital elevation model should be devoid of any depression. So if ever you find any kind of depression in that digital elevation model, before doing the surface hydrologic modeling, you have to remove all the sink or pits or depression. Only then can you determine the flow direction. But yeah, as I said, there are certain natural scenarios where if you have learned about this karst geomorphology, then like you might have gone through this topic where a river is flowing and then it goes into a hole and then it just disappears. So that is like mostly it's found and then it flows underground. So basically it's like as if the river just suddenly ceased to exist. So we have to basically remove that depression and see how it flows over the surface. So whenever we are delineating the watershed, if you like you remember the image that I showed right before. So whenever we are delineating the watershed, the first and foremost thing that needs to be done is to identify the pour point. Just like how, like of course we are like our primary objective is to remove the sink. Then when you start doing this working with the model, then first of all identify the pour point or the outlet. Okay. So usually these locations are mouths of streams or other hydrologic points of interest such as a gauging station. So most of the time it's the region where that stream is flowing out. So if we call it as like in case of river and all, we say river mouth or stream mouth. In surface hydrologic modeling, we specify the pore points. So the pore point need not be one, it can be more than one, or can use the stream network as the pore point. So we try to specify the pore point. If not, then we use the stream network to say that this is the pore point. This creates watersheds for each stream segment between stream junctions. Like we, sort of consider that junction as the like end point, and then so it will be a little more um, complicated. To create the stream network, first flow accumulation for each cell location is calculated. So we need to create the stream network, but in order to do that, for each cell, we need to see how the flow is accumulating. So here is an example of how the direction of flow is calculated. Just a minute. So here we have a input digital elevation model. So this is the input, and then we have a output over here. So we are having a 3 by 3 kernel over here and a coding system. So what do we mean by the flow direction? A conclusively definite line or course in which something is issuing or moving in a stream, where basically the direction in which the flow is happening. So we have a 3 by 3 kernel window over here. So this is the direction coding basically. Okay. So for the southeast direction, like sir said, we are coding it as 2. So these are just, codes rather than numbers. So you should not consider it as what do you say? Like, uh, you can't do any arithmetic operations. Rather, it is just a number which is indicating a code. That's it. So 2 is indicating the direction southeast. Then we have 4 is south. Uh, and then we have 8 which is southwest. So it's basically like if you consider the map like this is north, east, west, south. So this direction is southeast, southwest, northeast, northwest. So that's how that direction has been indicated here. So 128 over here means that the flow is in the northeast direction. So for example, like sir has given this example, so I'm just going to talk about this. So we have a 58 here, a 61 here, and a 68 here. Okay. So among these three, like 58, 61, and 68, 68 is very high. So the flow will be in the northeast direction. okay, in this direction, because 68 is high, which means like that value elevation value is 68, it is high, and the surrounding this is less, which means the flow will be in the northeast direction. Similarly, we can do for other things also, like for example in this case 61, so here 55, 47. So for this cell we have written it as 128. Okay, then let's say for this one 50, okay, just a minute, 64, and with respect to 61, so we have it to be in the southeast direction, so then we have a 2. Okay, so like this, based on the direction, like we are comparing the elevation surface, we are comparing the values, and then we are assigning the direction code to each of the cell. So flow direction, while we are calculating, we use this 3 by 3 kernel. I hope that is clear. Basically, what has been discussed is that we are given an input digital elevation model telling you like each cell has a elevation um, value. Like basically, we have values which indicate the elevation in each of the cell. Then what we did, we used a direction coding kernel. We applied that on each of the like cell, and then we got a output in terms of flow direction. The next one is identifying the stream networks. Okay, so stream networks can be delineated using flow accumulation theme. So flow accumulation in its simplest form is the number of upslope cells that flow into each cell. Okay, so by applying a threshold value to the flow accumulation, a stream network can be delineated. So we need to identify the stream network. So for that, we have to make use of the flow accumulation. And flow accumulation, basically what we're trying to say is the number of upslope cells that flow into each cell. Upslope means like downslope. What does that mean? From a higher elevation to a lower elevation. Upslope means from a lower elevation to a higher elevation. So the number of upslope cells that flow into each cell, that actually sort of helps you to understand the flow accumulation. So for example, to create a raster where the value 1 represents a stream network on a background of no data, the tool parameters could be like this. For example, threshold is equal to value greater than 100 cells. Like you're giving a threshold value. Like threshold value means a limit kind of thing. So in this case, this is how the flow accumulation is shown here. And the threshold is given as greater than 100 cells, right? Yeah. So here we have a relief model, a hillshade, which we discussed in the last session. So we have a hillshade, and then whatever this drainage that is there, that we are these blue lines is representing the drainage that you are seeing in the flow accumulation. Then we are talking about stream ordering, because like in the surface hydrological model, we need to also have an idea regarding the stream order. So this is done once you have the stream network with you. okay, like how that stream is spreading out. Once you understand that, then you can actually give the number or designate the number for the stream order for each of the flow like branches of that network. So for stream ordering, we have this Shreve method and the Stoller method. Okay, that is the main two methods that has been well established. So in the first method, that is the Shreve method, when the two links intersect, their magnitudes are added and assigned to the downslope link, like it is shown here. Like for example, 1 and 1 together, uh, like at the point of intersection, it is giving you another one. So that is 1 plus 1, that is 2. Then here 1 and 2 intersect to give you 3, because 1 plus 2, 3. Similarly, 3 plus 4 gives you 7. So that is how the Shreve stream ordering method is designating the stream order for the flow network. So the Shreve order is pretty simple and it is also very popularly used. But in the second one that you can see, like the Stoller method, so stream order only increases when streams of the same order intersect. Like for example, if 1 and 2 comes, then only the highest order is given to it. Okay. But if 1 and 1 are joining, like same order streams are joining, then it gets the next higher number, that is 2. So that is the difference. Like same thing only here and here, but in Stoller method, if you have the same number 1 1, same number means it was sort of like promoted to the next number, that is 2. But 1 and 2, then it will not be given the next number but rather the higher order number. So that is 2. Again here 2 and 1, so again we are having 2. But here we have 2 and 2, so it's getting 3. Shreve method is a little easier because you are just adding. Here you just have to keep in mind that only same order intersection will give you the next, like order will only increase when the same order intersects. Okay, it's showing that the call will end. Apparently, I think it is again scheduled for 1 hour. So I'll just quickly make another link and put it in the chat if you want to continue. Just a minute, let me just create it. I don't know, like only sometimes we continuously get the 2 hours, but at times this is the problem. I don't know why it's happening. But yeah, anyway, let's continue. So as I said, like we discussed about the Stoller and Shreve method, and the thing that you have to keep in mind is they are not the only stream ordering methods that are there. There are like 5 stream ordering schemes, but then Stoller and Shreve are the ones that has been implemented into the geographic information system. So largely, not largely, like it's widely used, like the Stoller and the Shreve method. Other than that, we have the Horton method, the hack method, and the topological method. So, as I said, like this, we have five stream ordering schemes in literature, but then like in GIS, we largely use the Stoller and the Shreve method. Okay, and in even in that, like as Sir said, Shreve method is a little more, slightly more used because it's quite simple. So here we have a good example. So we'll see how each of the numbering can be done, and then it's a bit easier for you to understand. Okay. So all the black ones like in Stoller order. So you have to remember, like in Stoller we are adding. Okay. And in Shref, like the similar ones are going to no, no, like in okay, stroller we are not adding. Stroller is basically like similar ones will give you the next higher order. And in Shref, we are basically adding. Okay. So here we have the stroller order and the Shref. So here I'll just mark this one. Okay, not all. We'll consider one network. Then that would be easier. So this is one. This is one. Okay. And in stroller, what will happen? Can you just tell me? Just a minute. Okay, so in stroller, basically I have a 1 here and a 1 here. Similarly, I have a 1 here and a 1 here. Okay, so in stroller, when similar numbers are coming, what happens? The next one will be the next higher order, right? So this will be 2 and this will also be 2. It's already color coded, so it's easier for you to understand. But even then, whenever you get a network like this and they ask you to determine the stream order, just remember this is how it is done. Now this is 1, okay? So this is 1 and this is 2. It's of different orders. So this is again going to be the highest order, that is 2. This is 2, this is 1, this is 2, so this is 2. Okay, here we have another one. Now 2, 2 together it's going to be 3. Here we have a 2, 2, 3 means it's going to continue to be 3. 1, 3 again it's going to be 3. Here also 1, so 1, 3, it is again 3, 1, 3. But here you can see 3 and 3. Okay, 3 and 3 together will give you 4. So that is how the stroller ordering is done. Now for the same thing, when you do the Shrev order, you can see here, this is 1, okay, and this is 1. And here, basically you can try from here. This is 1, this is 1. So 1 plus 1, this is 2. Then 1 plus 2 gives you 3. 3 plus 1 gives you 4. 1 plus 4, okay, so that is 4. Similarly from here, like, this is the main one. So that is going to be 4. And then wherever that network is joining, so there you are doing the stream ordering. I hope that is clear. It's a very simple example, but then just have to keep in mind the difference in how we are determining the stream order in case of the Stroller method and in case of the Shrev method. Now we are going to discuss about the flow length, like how we have discussed about the stream network and stream order. So next one is the flow length. So flow length is basically, it's an arbitrary pixel that is determined by summing the incremental distances from center to center of each pixel along the flow path from the selected pixel to the outlet pixel. And but since we are using a digital elevation model here, so as sir said, instead of using the term pixel, we can call it as cell. That will be more appropriate in this case. So it is the upstream or downstream distance or weighted distance along the flow path for each cell. Okay. A primary use of the flow length tool, it is to calculate the length of the longest flow within a given basin. So of course we have connecting flow and everything, but then the primary use of the tool in GIS, it is to calculate the length of the longest flow path which is present within a given basin. This measure is often used to calculate the time of concentration of a basin. So basically how much distance it has to travel, then we can determine that through this particular step in the surface hydrological modeling, because we are basically talking about the flow direction, right? So how far it has to travel, that can be determined in this particular step of the surface hydrologic model. And this flow length, it is often, as I said, used to calculate the time of concentration of a basin, and it is also directly linked to the flooding forecasting. So because you need to know the what do you say, the longest flow path, only then like it can help you determine like how far that flooding can affect, so you can forecast the flooding. It's also maybe related with sediment flow and maybe some other pollutants, because this is after all time of concentration. So it's basically how much time it would take to reach a particular location. Okay. So like as I said, it's used in the flooding forecasting, but in even when you want to determine the sediment flow, or you want to determine, like suppose some pollutant entered the water flow, so how far can it go? So such things can be understood when you study the flow length. So when like downstream flow, mm, okay, not the downstream, upstream option. Okay. So the flow length can be determined using the upstream option, like flow accumulation. As I said, it's for the upslope direction, right? So, and because this is a sequential processing, the surface hydrological model is basically like it's the fifth step in the surface hydrological modeling. And also this tool that is there that can be used uh, to create the distance area diagram of the hypothetical rainfall and runoff events using weight raster as an impedance to the movement of the flow. So this is the flow length for that digital elevation model that we had used earlier also. So drainage network with stream ordering, in this case they have used the stroller, and flow length are both shown in this diagram that we have here. Okay, flow length in the downstream direction, and you also have the stream network in terms of the stroller order. So as we go in this downstream direction, that you can see, like here we have the pour point, right? So this is the watershed, and here we have the pour point. So we can see like this is the low and this is the high. So flow length is highest over here, okay, and it is the lowest over here, which means this is the direction that it is coming, because as you come here the flow length is going to decrease, right? It's the pour point, it is the outlet. So that is how it has been determined here. So in case of downstream flow length, the minimum flow length would be at a pour point or outlet of watershed, and maximum would be at the watershed boundary, which I just showed you. Generally, the flow length assigned to the outlet pixel is 0, because basically there is no length per se. When it rains, a drop of water landing somewhere in the basin must first travel some distance before it reaches the outlet. So in such situation, basically like we can make use of this flow length. Next will be the watershed delineation, but I've not added it into this set of slides. So we will just continue with the slides that Sir had given. Okay, so we'll be discussing about the watershed delineation. Now, as I said, flow length is the fifth sequential, like in the sequential steps, it's the fifth one. And now we have the watershed delineation, which is the sixth in case of the surface hydrologic model. It is basically the determination of contributing area above a set of cells in a raster, and that is our digital elevation model. So the only requirement here is to decide the outlet. So once we decide where the outlet is, then or basically the outlet or the pour point, like once that is decided, Then the watershed can be delineated using the flow accumulation thing. So once the outlet is defined, then we already know from earlier regarding the flow accumulation. So basically that can be used in order to determine the watershed delineation. So you see, like if you want to define the watershed in terms of surface hydrological modeling point of view, then a watershed is basically the set of all cells whose downstream flow path passes through a selected outlet cell. So here you can see, right, this is the outlet. Like you have outlets here. So this is how it is moving down. The value of each watershed will be taken from the value of the source in the input raster or the feature PowerPoint data. So here we have a diagram doing the watershed delineation. Again, the same digital elevation model has been used. The watershed has been delineated and the condition of the threshold value was kept equal to more than 500 cells for the flow accumulation thing. So they have kept the threshold for greater than 500 cells. Like we are asking it to show us a watershed delineation by keeping in mind that it is like greater than or equal to 500 cells and nothing smaller than that. We have the flow accumulation theme in the background of this image, and then we have the watershed boundary here. One thing you have to keep in mind is like this threshold is given, right? So anything less than that 500 cells is not going to be accounted for. So as sir has mentioned, like we will have problems or limitations when it comes to surface hydrological modeling along the boundary or the margins of a input digital elevation model. That's going to be there, but then uh, keeping in mind all these assumptions and trying to make it as proper as possible, we can sort of um, let it be. This is delineation of sub-watershed. So here also, like you can, these ones that you can see, they are sub-watersheds. Okay, they are small, but if basically what you have to understand is this entire thing can be a large watershed, but within that large watershed, you can also have smaller watersheds like sub watersheds. Here, because it is a 500 cell threshold, it is showing you like this. 1000 cell threshold means it's going to give you a much more less complicated image output. So now there are other uses of watershed characteristics that can be utilized. For example, things like the shape, size of watershed, the physiography of the watershed, uh, climate, minimum, maximum, like the slopes and all those things. For climate studies, for drainage studies, land use studies, vegetation, all these things, this will be useful. So there can be many other things which we can use for watershed characteristics, but it once you have delineated the watershed or through this surface hydrologic modeling, the other parameters can be automatically derived. So these are some of the watershed characteristics that can be automatically derived from the DEM. One is the area, obviously, like when you delineate the boundary, then you will get the area, perimeter, the centroid, mean elevation, mean slope, the stream flow length, the length, the shape factor, and many more parameters. So how is this watershed characteristics used in engineering? So in case of drainage area, most important for hydrologic design, reflects volume of water generated from the rainfall. So the available water volume for runoff may be assumed as product of rainfall depth and drainage area. Because see, if the rainfall is very intense and the drainage area is less, then the chance of this runoff is more, and possibility of flooding therefore increases. Watershed length, it increases as the drainage increases, and it is important in hydrologic computations. It is defined as a distance measured along the main channel from the watershed outlet to the basin divide, okay, where that boundary is from there till the outlet. And this we have already talked about. And then when you consider both drainage area and the watershed length, that gives you measures of watershed size. They may reflect different aspects of size. The area can indicate potential for rainfall to provide a volume of water. The length can be used in computing the time parameter, like the travel time of water through the watershed, how much time it's going to take. So the size of that watershed and also the length, that is very important in order to understand how the water is going to be when the water enters via precipitation and all. Then we have the watershed slope. So flood magnitudes reflect the momentum of the runoff. Slope is an important factor in the momentum. It reflects the rate of change of elevation with respect to distance along the principal flow path. Then obviously the watershed shape also. Like I don't know if it's like you are already aware of it, but then there are different shapes for the watershed. So the shape, like for example, if it is tapering towards the end or if it's a little more bulkier, that kind of thing. A circular shaped watershed would result in runoff from various parts of the watershed reaching outlet at the same time. It is going to be like intense flow coming at in a location at the same time. That's not going to be very good, right? So the shape of the watershed is also important. Then we have the channel length, which is used frequently in hydrologic computation. So the distance measured along the main channel from the watershed outlet to the end of the channel. So that is also considered. Then we also have the channel slope, okay, which is calculated by this equation that has been given. So if it is not uniform, a weighted slope may provide an index which reflects the effect of slope on the hydrologic response of the watershed. And here we have a raindrop simulation or the shortest path route. So if I basically what we're trying to say is if we drop a single drop of water like this over here, then over a flow accumulation theme, it will show that which path it will flow to come out of this outlet. So that single one you're tracing, okay? So this you can do at once. You are having a flow accumulation theme as a drop simulation. And now major use of this is in related to point source pollution studies or also in use for estimating the groundwater recharge or other things. So this is a mass balance that basically we have using the flow direction and flow accumulation process. So we have the surplus water per cell, how much is the extra water that is present. We are calculating it using this mass balance. So the precipitation is, input precipitation is something which is adding the water. So P will be positive. Then we have the filtration, infiltration, and then we have the evaporation. These are all how the system is losing the water. Okay, so that's why they are given as negative. So based on this mass balance equation, we can actually compute the surplus water that is present in each cell. Now, predictive equations are another way to use for map overlay depending on for what purpose. If I want to calculate the water availability for runoff, then equation is used by the hydrologist to calculate the amount of water that will be available for runoff for a specific rainfall event based on the type of soil and land cover present at the location. And this information can also be used to predict the amount of water which is available for runoff at every cell in a watershed. And this could basically be accumulated over across a flow direction surface, and very important to the road engineers who has to design a road that crosses the drainage, because in flood events the minimum damage or no damage should occur, because you have like in flood events people have seen this roads collapsing, right? So if you know that that area is prone to flooding or excessive water exposure, then that needs to be known to the road engineers, and accordingly they can construct so that minimum damage, or ideally no damage, but then at least minimum damage is there. So if estimation has been done properly through surface hydrological modeling, then a proper design of a culvert or a bridge can be done. Because most of the flooding events, this is a big problem. Like sometimes what happens is if that bridge or the culvert collapses, then one region would be completely isolated from the other. There will be a loss of connectivity, which is going to be a problem for rescue and rehabilitation. So therefore, this is quite important. So here we have a flow chart. So regarding calculating the water availability for runoff calculation. Uh, so you have to bring the hydrological soil groups which as one of the input, because that's the soil retains the water, right? So depending on the soil type, that is going to change. Then the land use land cover map is important. Then we have the precipitation data, okay, and all of these combined you will have the runoff number, the surface runoff number uh, method, like you can just make use of that. And then you will have the water available for runoff and your elevation. Okay, so that is the digital elevation model. Then the fill depression sinks that we were talking about, elevation, fill depression sinks, flow direction, and then the accumulated water available for runoff. So these calculations are very important from a flooding point of view, modeling point of view. There may be many other types that can be generated using the digital elevation model. There are a variety of hydrological variables that can be generated using the digital elevation models. Flow direction grids are the basis for a wide range of dynamic modeling tools. Then we have the topographic wetness index. So it is also called as the compound topographic index, CTI. It is a steady state wetness index. So in some areas it is shown in shown to predict the solum, that is the surface and the subsoil layers depth, and it involves the upslope contributing area, a slope raster, and a couple of geometric functions. So here we have a diagram. So this is the output based on the digital elevation model that we were using before. Here it's the see that's what, like, depending on your requirement, the classes are being varied, right? Earlier we had the downslope direction, that kind of thing. Here we have the wetness index. So darker means the more the wetness index is. Okay. So as you can see that darker here, uh, it is the main higher order stream where you get all the water, and you're having this wetness quite high over in these locations. And there are areas where that value is like less, where you have light pink color. So that is like telling you that the wetness index is less in that area. So application of this topographic wetness index, it is to study the runoff, the flood, soil erosion. So when you calculate the topographic wetness index, the value of each cell in the output raster of topographic wetness index, or the CTI, is the value of flow accumulation raster for the corresponding digital elevation model. Higher this topographic wetness index, that represent the drainage depression, because that is where you have a lot of water. So obviously wetness is going to be higher. And these are the drainage lines that you're seeing here. Lower values represent the crest or ridges, because that's a slightly elevated region where water is not going to stay. It might come be there a little bit, but not as much as the depressions. So we can basically understand that where this light pink color is there, probably those are ridges, and these are depressions where you see the dark lines. Then we have the sediment transport index. So that is basically, what does sediment transport mean? It is the movement of sediment, typically due to a combination of gravity which is acting on the sediment, and the fluid in which the sediment is entering, because sediment as such is not going to go, right? So gravity needs to help it, and also the fluid carrying that sediment. So it occurs in natural systems where the particles are clastic rocks, like you have sand, gravel, boulders, mud or clay. Fluid can be air, water or ice. Okay, like these all can be carriers of the sediment. And the force of gravity acts to move the particles along the sloping surface on which they are resting. So fluid motion, sediment transport basically occurs in the rivers, oceans, lakes, seas and other bodies of water due to currents and tides. Like river current, if the flow is very intense, that is going to take a lot of sediments. So here again we have a digital elevation model showing you the sediment transport index. It characterizes the process of erosion and deposition, because where you have excessive sediment, that is going to be the deposition place, and then where you have the like lesser sediment, that's going to be the erosion, representing the erosion. So it presents the effect of topography on the soil loss, and it can vary along the length of a stream. So this is mainly applied to understand soil erosion in a place. It is important in while you study the sedimentary geology, geomorphology, civil engineering, and environmental engineering fields. Okay, understanding the sediment transport. It is most often used to determine whether erosion or deposition will happen, and how much of erosion or deposition can happen, and the time and distance over which it will occur. Because if it's a very um, higher index, then that means it's going to happen in a very short duration, and so such things needs to be understood. So an example that sir has also mentioned is like in the Himalayan terrain, we have the Tehri Reservoir. I think it's in Dehradun, Uttarakhand or something like that. So if you want to estimate like what kind of sediment is going to come into the reservoir, because you know that sediment will definitely come, right, from the river flow. That is going to reduce the storage capacity of the reservoir. So ultimately, that is going to affect the power production. So that estimation of sediment transport is very, very important in this aspect. Not just this, but other things also, but this is a good example for that. Then we have the stream power index. So stream power, it is the rate the energy of flowing water is expended on the bed and banks of a channel. Bed means river bed or stream bed, whatever, and channel is on the both side. Like no, like yeah, banks of the channel. It is the potential for flowing water to perform geomorphic work. Geomorphic means, you know, act that water affecting that land area and all those things. Stream power can be calculated using a digital elevation model. So this is how stream power index is determined based on the catchment area and the gradient. So as this catchment area and gradient increases, the amount of water contributed upslope, like by that upslope, is going to increase. Velocity is going to increase, stream power will increase, and erosion risk will also increase. Stream power index, it controls the potential erosive power of overland flows, thickness of soil horizons, organic matter, pH, silt and sand content, plant cover distribution, and all that. So here again we have a digital elevation model which is showing you the stream power index. So it's largely like very less in these areas, but you can see very like not so clear, but here you can see the darker lines. It's an indicator of erosive power of overland flow. So it's mostly along the channels. That's why here you can see that dark color. Okay, so that is all for today's session. I have not discussed any problems because we had discussed that in the last session, and the week 11 solutions are not yet out. So hopefully like we can discuss that plus the week 12 in the last upcoming session. Okay, so with that I'll conclude today's meeting, and thank you for listening patiently. So yeah, thank you.